Okay, this is section 4 of chapter 18 and it's one of the most descriptive parts of the chapter. It is based around the descriptions you need to put in before the mathematics. Now, a lot of the thinking behind this actually fits in really nicely with one of the Java applications on PHET. If you download the AC and DC circuit labs, this works really nicely. So we're going to look at two aspects here. One is the circuit we've been looking at so far, which is discharging, but we also have a charging circuit. And for both of them, you're going to need to be able to use the equations to work around it. Now, we have here the circuit we've been using so far, so we can turn it on, and if we click it shut, we can make things work and charge up capacitors and things, and let it discharge. So we have a discharge circuit. Over here we've got a charging circuit. Now, if we show the electrons and what the charge is happening, then we can get our head around the descriptions, and we have put in that description in the notes. Now, you cannot see any of this happening. That's the whole point of having applets like this, so you can play with them. But what we can do is we can take measurements from this. So what we're going to do is we're going to stick in a current measuring device here and there. We'll put that in a second. So we'll just leave that out of the way at the moment. And also what we're going to do is stick in a voltmeter. So our voltmeter can tell us what's going on, and in the circuits we played with, what I can do is actually find out what's going on by playing around with a real voltmeter. So I'm going to show you real practical later to go with our next section, but this is just to get your head around the ideas. So on the circuit here, if we close the switch, then we've got current flowing through our bulb. As you can see, I've limited it with a 20 ohm resistor, and you can change the values of these, you can play around with them a little bit. Point out I've got the same resistor on this circuit, so I've got the same components, just this one has a discharge circuit. So we've got 9 volts on here, and we have a certain current flowing through it, which we'll look at in a second. But if I open the switch, then all we've got is charge being able to discharge from here, and our voltage drops as we get less and less charge on here. Okay. Now, one of the experiments I'm going to get you to do is to take a time lapse of one of these in real life and plot that over time, and it'll lead us nicely into the ideas of exponentials that we're going to do. Now, to see what that's doing, what I'm going to actually do is stick a current reading on as well. Okay. Now, at the moment it's quite dead because we haven't charged it up. Here we go. So, going to make that graph bigger for you. Okay, so we've got around about 0.3 amps flowing through this circuit at the moment. If I let it discharge, then you can see the current itself slows down. So the electrons are going slower, but the actual current flowing gets lower. Okay, so the rate of flow of charge is slower, therefore you've got a lower value of current until near enough it equals 0. While it's been doing this, you've actually got the same shape of voltage. Okay, so even if you cannot see the electrons, you get the same effect. Put it back up again. Okay, so we have our current flowing. You can see our lamp is giving out some light. It's not very bright for you, I suspect. But as we discharge it, then that drops really rapidly to start with. It's dropping rapidly the current. And then as this slows down in its dropping, then the current reduces in size as well. So you can see the charges disappearing off here, but you can't see the value of voltage. But think about what's happening. The reason we've got a current flowing is the voltage on the capacitor is dropping. Now, what I can do is we can change this around, and we can do the same thing over here with a capacitor that only charges up. So I'm going to stick my voltmeter on here. Let's just move it across to make it a little bit easier. I'm going to monitor the current flowing through the wire, only this time we are charging through the same resistor onto the same capacitor. So we've put it on, Again, big spike of current, but then the current drops. But this time the voltage is getting bigger. And the reason is the charge is filling up on this plate, and it will keep filling up until we have no more potential difference between the cell and the capacitor. Okay, and then by that point there's no voltage difference, so no current flows. If I open up the switch, it's going to stay charged up, so I need to have a little discharge circuit here. There we go, and we can let that all leak away. Okay, now it's not going through the current meter, but it is affecting the voltage on our capacitor. Okay, so that's near enough dropped to 0 volts. There we go. So let's just split that junction and put that out of the way, and let's look at it again. Okay, so I shall reduce the size of the scale slightly, close that, and again look at my graph down on bottom left. Okay, so big spike, and then exactly the same curve as we had before. So we had a maximum current, and then the current gets less and less and less. So the rate of flow of charge onto our capacitor is the same as the rate of flow of charge off our capacitor. Okay, and that's a really important fundamental idea. So load this up, have a play around with it. If you take the resistors out of the circuit, then it just gets you a faster decay because current can flow at a higher rate. Charges can flow through smaller resistances faster. And if you just have the bulb, you'll see the difference in it. So have a play, charging, discharging. Just use the bulb as your resistor. I should say, if you right click in any of this model, you can change values as you're going along as well. Okay, so some great thing to play around with. Good to get your head around electric circuits again as well. So in the PHET applet, you can see all this happening, but to just remind you, this is from Section 1, you cannot use this in the exam. And the reason is you cannot see any of this happening in real life. So what we need to do is get discussions, get ideas, get descriptions that fit in with stuff we can measure, voltages, currents, etc. So this is going to give us a whole set of graphs, and it's going to lead us into the two equations that describe the two processes. So step 1, realistically, we will have a battery with internal resistance. Okay, so here's a single cell in this diagram. It doesn't matter if it's cell or a battery. Over here you've got your load, whatever that is, some sort of large resistor, and then capacitor going on. So the only way to see what's going on is to draw yourself, connect yourself in real life, a voltmeter across the capacitor. If we put it across the resistor, it will give us the same value when discharging. If you put it across the battery, it'll give you the same voltage when charging. However, if you put it across the capacitor, that's the only one common to both circuits, so it's the only one that will give you the true reading all the time. Okay, now just have a read through this and have a think about this. It's mentioning electric field and so on. But when you get down to here, when you're moving each electron onto the negative plate, it's all to do with that crucial capacitor equation. Okay, so Q is proportional to V. Okay, so Q equals CV. So as the charge builds up, so does the PD. So by measuring voltage, we can tell what's happening inside. We can infer what's happening inside, but we can't see it. Okay, but we can talk about the rate of flow of charge because we can talk about current. We can talk about current flowing through the resistor, so you could measure voltage there as well. Okay, so you could do that. It doesn't really matter too much. But the key idea is that whenever we start charging up, in this case, so for charging capacitor, whenever we start it up, there's no opposition here, there's no voltage here. So the only thing driving the current is the output voltage of your cell. Or in other words, EMF subtract whatever's lost here. Now, as the charge builds up, okay, and this is crucial for your own understanding, bit extra in the exam answers, but as the charge builds up and the current slows down, as this fills up, in the end, as long as there is a difference between this and this, current will keep flowing. So actually, when this is full, you will get the voltage of the EMF equal to the EMF. You won't get the output voltage, because if you remember back to last year, the output voltage of a battery is always less than the EMF because you lose voltage here, but you only lose voltage here if you've got a current flowing through it. So if current has stopped flowing, there's no energy loss in the circuit. All of that charge that's been pushed will give a voltage equal to the EMF. Okay, so let's go on to the main bits. Okay, so as there is a large current, I'll just put in, just to give you that extra little detail, as R is small. Okay. Right, so when we go on, the description of why things flow then is actually about voltage subtract voltage. Okay, and that's the way to think about how to explain things. So if we take EMF, okay, of the battery, we subtract the voltage of the capacitor, so that's the difference in voltage, then that will give you your current flowing through your little resistor. So that's in this circuit here. Okay, so if you always argue it through in terms of this, you'll never get it wrong, because you can measure all of those things. Okay, so as we saw with the little animation, and as you'll see with the practicals, our current is maximum to start with, because there's nothing here preventing the flow, so it's really big, and then it fades out. And the reason it's fading out is because as this gets bigger, as this value gets bigger, the difference gets smaller, so the current gets smaller. Okay, what's happening in the capacitor? Well, the capacitor is charging up. Okay, so effectively what we've got going on is this charge on the capacitor leads us to the rate of flow of charge. Okay, so linking in with a little bit of maths here, dq by dt. Okay, so that's causing that. But if we think of it the other way, again using our class equation, the key equation, well, changing charge will also change voltage. So what we've got going on to this one is V is Q over C, okay, or Q equals CV. And so they are proportional, so we will get exactly the same shape of curve, if you draw it well, and that shape of curve, which we're going to explore next lesson, has a constantly changing gradient. It doesn't matter which one I put this on, but the gradient gets smaller and smaller. Okay, so for the same drop sideways or jump sideways, our height change there gets less. And if we do it on this graph, you'll get exactly the same gradients. It'll just be negative rather than positive. Okay, but again, those same gradients at those same moments in time will give you those same values and therefore the same shape curve. Okay, now that is for the idea, just to kind of simplify this, because I know this is a bit of a messy diagram sometimes. This is all to do with that main idea of having you know, a single resistor and a single capacitor. So this, I'm going to draw it over, squeeze it in the side here, is effectively, for that equation, I have my, let's do it this way, so little resistor at the top, here's my EMF, okay, so that's my lost voltage, and effectively what I've got going on is my capacitor. Make sure it looks different from your cell. Has a voltage there. So voltage of the capacitor, this is going to be voltage of the little resistor, which is I little r, that's I times r, whereas that's little subscript. Okay, so basically what we've got is Kirchhoff's laws. We're adding up the voltages and they'll always equal the EMF. As one gets bigger, the other one gets smaller. Potential divider circuit. Okay, if we go to a discharge circuit, then actually what we've got, and a little bit of place over there, so we've got a little bit, space at the bottom, is we've got a much simpler circuit, and so the mathematics of it is simpler. In this one, all we've basically got, and again it doesn't matter too much which way round we do it, but we have your capacitor, which will have a voltage on, because you've just charged it up, and that load resistor, and effectively that's it. Put a voltmeter in to measure things, but actually you're going to end up with voltage there is going to equal, again of course, I times R, just times, it's a big value of resistance this time. Okay, so that's your drop across there, that's your drop across there. The mathematics is far simpler, and so because of that, if we can get this cleaned up, we just simply have voltage as capacitor equals IR. Okay, so they are proportional, there's no subtraction like there was before. What does that mean for your graphs? Well, it just means your graphs are a bit simpler. Okay, so if I move down to here, I've got a current dropping just like I did before, but is going from the negative value. Okay, so I'm going to pick up on some terminology and label up these diagrams in a second, but why is it negative? Well, when we were filling up our charge, and again I'm going to go with conventional current, this was your current flowing that way. Okay, so you ended up with a positive charge and a negative charge that way round on your capacitor. When you flick your switch and it's discharging, again conventional current, it's going to go that way. So it's going downwards onto the capacitor, and then when you flick the battery to discharge, it goes upwards off the capacitor. So you've got current flowing in the opposite direction. So in terms of graphs, it goes in the opposite direction too. Exactly the same shape, because it's controlled by the same thing, but the gradients will be different because this time it's flowing through a big resistor rather than a little resistor. So, same idea. What's going on with that? Well, again, we have our charge, but this time we have emptying. Okay, because it was full at the beginning and it's going to empty. Now, if I compare it what I had before, which I'll do as a dotted line, ish, not bad. What we've got is the mirror image of the curve. Okay, so again, the same characteristics, it's just doing the opposite. So charging curve there, and that's the discharging there. Okay, now if we think about it, what they give us, if you add them up, let's just change the dots there, is they'll end up with a certain value, and that certain value we call Q0. So the symbolism we use, that's your maximum charge, and it doesn't matter if it's flowing on or off capacitor, it's going to still be the maximum charge. Now why that is important is if we relate it back, again giving us our current, well, we end up with again a value of I0, a maximum value, but at some other point I will be obviously less and less, because 0 is at the top on that axis. Similarly, Q equals CV, so from here our discharging voltage drops in the same way. Now, I'm being really obvious with this because our equations that you need to be able to use are charging and discharging exponential equations. They're exactly the same equation, but one is subtracted from this maximum value to give you the other one, and you'll see that in the equation when we do that in our next lesson. Okay, so it's a really nice way of thinking about it. They add up to your total charge. Right, so in the exam, perhaps this is a bit more like some other exam boards. AQA, OCRB do a lot of this description stuff, maybe a bit less for us. However, describing it gets it right in your head. What I would suggest you do is thinking about just what you can measure in a circuit, have a go at describing this. So pause the video and try this answer yourself. Okay? Okay, these are the steps in my answer. The video cut out, so here's one I prepared earlier, as they say. Key points. It's the voltage in discharging. Just made that clear. It's the voltage that's driving the current. So the potential difference on the capacitor drives current. Imax equals V0 over VR. So think of V0 as V of the capacitor. Okay, so capacitor divided by resistor will give you that. So at the maximum value, you'll end up with I0. Okay, as the capacitor discharges, as Q floats out, then because Q equals CV, V drops proportionally. Okay, and so because, again back to that equation, but the capacitor voltage is now dropping, so the potential difference is less, so there's going to be less current, so the rate of flow of charge decreases. Okay, so cause and effect there is really nice and clear.